So, dear participants, again welcome back. In this session, we are having speaker Dr. Ambika Prasad Shah. I am happy to share that he is the alumni of IET DAVV itself. Dr. Ambika Prasad Shah is currently working as an assistant professor in Electrical Engineering Department and Associate Dean Corporate Relations at Indian Institute of Technology, Jammu, India. He received BE and ME degree from IET DAVV and PhD degree from Electrical Engineering Department, IIT Indore. Before joining IIT Jammu, Dr. Shah worked as postdoctoral fellow at the Institute for Microelectronics, TU Vienna, Austria. He has co-authored more than 60 research papers in peer-reviewed international journals and conferences. He is the fellow of IT, senior member of IEEE, and lifetime member of ISTE, ISCA, IEI, and IAENG. His current research interest includes reliability analysis of digital circuits, design for reliability, fault-tolerant circuits, reliability modeling, low-power, high-performance circuit designs, and hardware security. So I welcome, sir.
Okay, so thank you so much, ma'am, for the nice introduction, and it's really honor for me to give some talk at IIT and coming back again. Like initially, I was there and I was a student, I was a teacher, so it was a pleasure. And again, giving a talk at IIT DAV is a very good thing for me.
Yes, it
So
is
before
really
this,
nice experience for us also.
yes, so I will try to connect, like, see, the theme of this FDP is related to the cyber security. So that is completely related to the software side. But I will try to connect the why hardware security is important, especially if we are targeting the software security. So let me share my screen, then we can continue the session. I think you may be able to see my screen now. Is it?
Yeah, it is visible.
Okay, perfect. So now I'm making it full screen, and then we can start it. Okay, so thank you. So actually, as I told you, like the theme of this particular FDP is like cyber security, and I will be discussing about the reliability, security, and quality of integrated circuits.
Sir,
And
Shah, sir,
yeah, please.
just a minute. I would like to say to participants that we will give 15 minutes for discussion session. So please be ready accordingly. Okay, 15 minutes, last 15 minutes for discussion session. Please continue, sir.
Yeah, please. So yeah, I will be happy to have some your query on chat box itself. So please post your queries, and at the end we will see all the queries, and I will try to answer all those questions. So okay, so as we are dealing with the cyber security, and this is really very big challenge nowadays, and cyber security remain a critical fundamental of the digital world, where the people are dealing with the software security, hardware security, and that need to be considered, especially if we are considering the data where that need to be secure. Everyone want to secure their data, and in that case, definitely the security is one of the prime concern nowadays. Okay, but over the year, hardware security has received very limited attention. Most of the focus was on the software security side, but nowadays the hardware security becomes also one of the prime concern, because the only and the important thing is, like the whatever the software we have, that can be patched if there is some problem, there is some constraint, there is some threat on the software, that can be patched, that can be solved. But the real problem comes if you're talking about the hardware security. Whatever hardware you have, once it is tracked, if there is some problem in the hardware, that cannot easily be tracked. So it is really very important during the design time, when we are designing some integrated circuit for any application, whatever we have, we must be sure about how much reliable it is, how much secure it is, how we can do, how we can improve the security of this, whatever the hardware we have. And if we have the secure hardware and we are utilizing those secure hardware for our application, then we can say our data is secure. So I request participant to mute yourself, so that may disturb me. So I request you to please mute yourself, and that will be better for me. So I was talking about why the hardware security is really important. But other than this hardware security, there are two more important things like reliability and the quality. There are many things that need to be considered, because the security circuits, whatever we will talk about today, that also depends on the circuit reliability. If our circuit is reliable, and if it is perfectly working with respect to time, and if there is no trapping on it, there is no effect of the stress and everything, then we can say that we can enhance the security of that hardware chip. Okay, so the hardware reliability, hardware security and the IC reliability, these two are the interlinked. And the quality, like the process variation, temperature variation, effect of supply variation, and everything that can also alter the performance of the security chips. Okay, so the important thing that need to be considered, like the reliability, security, and the quality of chip is really interconnect with each other, and that is well aligned with the cyber security. Because if you want to secure your data, in that case, whatever hardware you are using to secure your data, because see, directly with the software you cannot do anything. You need some processing unit which is needed as a hardware side, from the hardware side. And that if the hardware is secure enough, then we can claim that, and we will be sure about the security of our data. So this is the basic motive of this talk or this lecture. So how we can interrelate the hardware and the software security. Briefly, I will also talk about, okay, so this is my content of the talk, that I will start from the introduction. I will talk about some reliability issues. Why I will talk about the reliability issues? Because some of the reliability issues, they are problem if you are considering the reliability. So see, reliability and the security, these two are the different ages of the resilience, circuit resilience or system resilience. But if you are talking about the reliability only, so this PVT variation, BTI, and these all other parameters are the problem. And we have to minimize these problems if our goal is to design a reliable circuit. But the funny thing is, I will tell you in the detail later on, that if any of the chip has some process variation issues, like bias temperature instability issues, so this kind of problem can be utilized to secure your hardware. So this is really tricky job, really funny thing, that the problem in one domain like reliability can becomes the benefit in other domain, that is the hardware security. Okay, and I will try to connect if there is some reliability issues with the ICs, then that reliability issues can be utilized as a benefit to secure your hardware. Okay, so this is the very important thing, and I will discuss about these things. So I will talk about some reliabilities, and this is the reason why I am considering the reliability issues in the integrated circuits and systems. Then I will talk about some hardware security issues, and I will talk about some hardware security primitives like physically unclonable function, true random number generators, counterfeit electronic, hardware trojan. So these are some of the major hardware security primitives. There are some more hardware security primitives, but these are the important one and that need to be addressed. Okay, and then I will talk about, like here many of the participants are researchers, teachers, so they may be knowing what we can do in the, if I'm interested in research, and if I want to continue my research in the reliability side, so what are those challenges where we can work, and what are the topics that need to be considered for nowadays. And similarly, that I will also discuss about what are the different security challenges and what kind of the problems that need to be addressed if my target is the security one. So this is how I will try to relate the reliability and the security. There's one more term like Quality, yeah, definitely the quality that depends on the certain things like I have already told you, like the process variation, manufacturing defects, if there is some soft error. So these kind of things comes under the quality segment. Okay, so we have three different domains: reliability, that I will tell you. Then I will talk about some security, how we can utilize those reliability concerns for the security applications. And then I will also talk about how to maintain the quality of IC so that we can have the better reliability, so that we can have the guarantee on security. Okay, so this is the brief outline of the talk which I am going to cover in this particular session. So keeping these things in our mind, let us start with the reliability. Okay, so as we know that with the technology scaling down, the integrated circuit feature size has been driven into many physical limitations. So see, if we have a long channel device, and if we have some dimension of that particular transistor, so if I want to embed more number of transistor on a single chip, if I want to increase the density of the transistor, if I want to increase the functionality, in that case, what we have to do, we have to miniaturize the transistor. We have to scale down the transistors. And the important thing is we cannot directly miniaturize or directly scale down the transistors. We need to take care of certain rules and regulations. And there are two important rules for scaling, and that first one is the constant voltage scaling, and the second one is constant field scaling. Okay, so the constant voltage scaling means where we are fixing the voltage and all other parameters are going to be changed. And in constant field means the electric field across this channel, whatever the channel we have, that need to be constant and other things need to be changed. Okay, so these two are the scaling techniques. But the very important thing is, if I want to scale down the devices just to increase the density, we cannot do it directly. It is not like we have the 10 nanometer transistor, then if I want to increase the transistor by 2 times, then we just reduce all the sizes by 50%, like 5 nanometer. It is not that much easy. Okay, so we have to maintain like the electric field, we have to maintain the performance parameters as well, because whatever the performance was before scaling and after scaling, that should match. Okay, so and the trend, whatever we need to follow, that should also match. Okay, so we need to find certain rules. But the important thing is, once we have started scaling down the transistors, in that case, some secondary effects comes into the picture. For the long channel devices, those problems were not that much important. But if we scale down the devices, those things comes into the picture and might be they start affecting the performance of those devices. And here, those problems are like reliability issues. So I will discuss about all those things in detail. We have the sufficient time, 2 hours, and I have only 37 slides, so I will take too much time on explaining each and every slides. So the important thing is, like, if we are scaling down the devices, the oxide thickness is reduced by 30% in each next technology generation, and this is really very important thing that need to be considered. If the oxide thickness is reduced by 30% for next technology generation, there is a probability of charge trapping from the channel and the gate material, whatever we have, polysilicon. Okay, so there is some trapping probability can happen. So what those trappings are, I will discuss in details, and how those trapping can be utilized for the security purpose, I will also try to interlink with them. Okay, so it seems like this particular lecture is something different from the theme, but after the end of this session, I'm pretty sure that you will find something important, like how we can have some hardware security, and that is really very important. Okay, so considering these two things, reliability and the variability issues are the biggest design challenge, especially if my target is for the high speed applications. Okay, so in the same set, in order to keep a technology scaling down, two important things that need to be considered, and the first thing is like excessive leakage power, And the second thing is device or the circuit reliability. Okay, and if I'm considering the reliability side, so the PVT variations are one of the serious issue for the scale technology generation technologies. One very important thing is if I'm talking about the reliability, so there are two types of reliabilities, a reliability concern. The first one is which can affect immediately once the chip is on. Okay, and the second kind of reliability is if I have operated our chip for the longer time period, and with respect to time, some of the degradation mechanism comes into the picture with respect to time. Okay, so the reliabilities are divided into two categories. The first one is time independent and the second one is time dependent. So the PVT variation in other kind of things like process variations comes under the time independent, that can happen during the manufacturing time when we are fabricating the chip. But there are some mechanisms, there are some phenomena that comes into the picture with respect to time. Okay, so and those temporal degradations are the bias temperature instability, hot carrier injection, and the time dependent dielectric breakdown. I will talk about how this bias temperature instability can be utilized to secure or to check whether the hardware which we are using is secure or not. Okay, and whether it is replaced one or it is remarked one, so that can be detected by this bias temperature instability. Of course, this BTI is a problem, especially if you are considering the reliability, but there's the same BTI kind of phenomena that can be utilized to identify the clone chip. If some chips are cloned, either the chips are used or it is counterfeited ICs, then those things can be detected by this bias temperature instability. So I just told you in the beginning, like the reliability and security and the clubbing, these two things are very funny thing. So considering one parameter, one of the corner is if our concern is in one of the corner, then the second will automatically be solved. Okay, so that I will connect each and everything. Apart from these things, there is one more reliability concern that need to be considered, and that is the soft error issues. What happens if we are using our ICs, our chips in the harsh environment, especially like the space applications, where the probability of high energy particles are very high. So those high energy particles can penetrate into the bulk of the semiconductor devices. And because of those semiconductor devices, there is some generation of secondary electron hole pairs, and those secondary electron hole pair that can be collected at the sensitive nodes. And because of this phenomena, there could be some probability of logic flipping. So whatever the data we have stored on the memory or any other places, due to this soft error, that data can be flipped. And this is also one of the serious concerns that need to be considered. So we have to design our chip in such a way that the effect of soft error should be as small as possible, so that the probability of flipping can be reduced. So if the probability of flipping is very less, then we can say like we have the reliable chip. And if the chip is reliable, we can utilize it for the security applications. So this is how these all things are interrelated to each other. Okay, so yes, this slide is going to be very important because see, if you talk about the different ages of the circuit resilience, so there are three ages. The first one is the integrity, second one is the availability, and the third one is the confidentiality. Whatever the circuit and system we have, if any of the circuit or system is very good in any of these things, like either in integrity or in availability or in the confidentiality, we can say that we can rely on those chips, we can rely on those systems. Okay, so if I'm talking about the confidentiality, so the confidentiality means that is important if you want to protect your data. Okay, so if you are confident that whatever data I have stored on the hardware, that is secure enough, that cannot be trapped, that cannot be attacked, it cannot be there is no trapping, there cannot be some Trojan that can be inserted in between. Okay, so if we are secure enough and if we are confident enough that the chip whatever we have fabricated and that cannot be trapped, so we are confident that we can utilize it for the security applications. Okay, and subsequently for the cyber security kind of things. So the chip which is vulnerable to the attacks and other things, that is a problematic if we are considering the cyber security. But if the chip is protected from the problems or side channel effects like tampering, like hardware Trojan, Trojan insertion, something like that, so we can say that we are confident enough that the data will be secure in that particular chip. Okay. The other thing is like the integrity. Integrity is really important. Like whatever the data you have, that need to be preserved perfectly. But whatever the data you have, that can affect in two ways. Either if there is some interference between the two devices or two different modules, whatever is there inside the chip, there is some process variation that can also affect the performances. Environmental noise can also affect the performances. Okay, so these things which you can see in the yellow box on the integrity side, these all are the part of the reliability. Okay, so if there is any of the component is present in the chip, and if there is some effect of anything in the chip, then we can say that the chip is not reliable. Okay, so the important thing is for the reliable chip, you must have less interference between the two devices or two modules. We must have less effect of the process variations, and we must have less effect of the environmental noise, external noises. Okay, because the external noises may create the problem in trapping the data. Okay, so if these all are not present in a chip, we can say that the chip is reliable. So this is the part of the integrity. Okay, the second important thing is like if you talk about the second is like the second segment of the three edges, and the second segment is like the security. So on the integrated side, there could be some accelerated aging. I was discussing about the bias temperature instability, hot carrier injection, and the time-dependent dielectric breakdown in the previous slide. So those all comes under these aging effects. Okay, so these aging effects are the problem in terms of the reliability. But those aging effect can be utilized as a benefit for the security application. So I will tell you in details. So these are something like if we have some, if there is some chances of fault injection, so you cannot rely on the integrity of those chips. Okay, and if there is some possibility of tampering the hardware, so this is also the question mark on the integrity. Okay, so if we are considering this second edge of this resilience, so you need to consider the security as well in terms of the accelerated aging, fault injection, and the hardware tampering. Okay, so that these red boxes comes under the security components, and the yellow boxes comes under the reliability components, and they are interlinked with each other. Okay, now and the third one is like the availability. Okay, so the promote the availability of data for authorization use. So if everything is perfectly fine, if the authorized user are accessing the hardware and anything, so you can say that the data is available to the authorized user only, but the other people cannot hack it, like the denial of service attack. If there is some presence of denial of service attack, so there is some question mark on the availability or the authorization. And other than these things, like there could be some attack on the control flow as well. So these two things comes under the insecure kind of effects under the edges of availability. And if you talk about the reliability on the availability edges, in that case, the fault injection, like transient fault, intermittent fault, permanent faults, due to either the reason could be anything. Either it could be the software or the data corruption and anything. So the reason could be anything. But if there is some fault, so you cannot say like this is the authorized user who are accessing. So if the unauthorized user are accessing, then they may create a fault on it, and that can create the problem on the reliability of those chips. So these three are the different ages of the circuit and system resilience and the interrelation between the reliability and the security of chip. Okay. So in case of any doubt in any of the topic, you may write your query to the chat box. I will check it out later. Now, the important thing is if I'm talking about the reliability. So initially, I will start with the reliability issues. Then later on, I will talk about the security issues. Okay, so basically, as I already told you, the reliability mechanisms or the failure mechanisms are divided into two categories. The first one is the time zero one, and the second one is the time dependent one. In the time zero one, there are two types of the reliability concern or the process variations. The first one is the intra-die process variation, and the second one is the inter-die process variation. If I'm talking about the intra-die process variation, the process variation can be at the both end. Either it could be at the front end or at the back end side. And if I'm considering the front end side, there could be the problem like RDF, which is the random domain fluctuation, LER and LWR, which is the line edge roughness and the line width roughness, and the third one is the OTV, which is the oxide thickness variation. Okay, so these three are the parameters that comes into the picture, especially if we are scaling down the devices. So at the lower technology, the effect of all these intra-die variations are very high, and that need to be addressed properly. If these kind of problems are not addressed properly, we cannot rely on the reliability of those chips. Might be the performance may vary with respect to the time or any other things. Okay, so this is the serious concern that need to be considered. The second segment of this process variation is like inter-die process variations, where we can consider lot to lot, wafer to wafer, and dia to dia. Okay, what this kind of variations are, I will discuss in detail in the next slide. The second segment of the reliability failure mechanism is like time dependent one. The time dependent that divides into two categories. First one is the environmental one, and the second one is the temporal degradation. Okay, that we also call it the aging effects. Okay, so first let us talk about what those environmental failure mechanisms are. So what happens if we are operating our chip in certain conditions? So might be if the conditions are changing, might be there could be some fluctuation on the voltages. Okay, so if there is some fluctuation on the voltages, might be the performance of those chips will also affect. So that will also be affected with the voltage variations. Okay, and that need to be considered. Temperature variation is also very important. Like if we are operating our chip at certain temperature, and if we are changing the temperature from T1 to T2, so the performance of those chips will also change if I am changing the temperature. So how we can relate these performances of the chip with the temperature, I will tell you in the details later on. And the third and very important thing, which I have already told you, what the soft error is. The software is nothing but if we are using our chips in the harsh environment, especially on the special applications where the probability of high energy particles are very high. In that case, those high energy particles can affect the performance, and they can alter the logic. And if they can successfully alter the logic, there will be some error and there will be flipping. Okay, so in presence of high energy particles in the harsh environments, the probability of failure also increases. So this is the first segment. On the second side, which is a time dependent one, and the second segment is like temporal degradations. So for that, these aging effects are divided in either it depends on the back end and the front end also. So if we talk about the back end side, it is the electromigration, and from the front end side, I have already told you these are the BTI, SCI, and TDDB. Okay, so I will discuss all these things in detail in the later slides. So this is the complete classification of different reliability failure mechanisms. Either it is time dependent or time independent. Yes, this is really very important. And why I am repeating these things again? Because some of the reliability concerns are a problem, especially if you want to design a reliable chip. But those reliability issues can be a benefit, especially if we are talking about the security concerns. Okay, so this is the important thing that need to be considered. So let us talk one by one. The first one is the inter-die variations. As I already told you, there are two kind of variations. The first one is inter-die and the second one is intra-die. And we also call them global and the local variations. So in this particular figure, if we can, yeah, so let me use my pointer first. Okay. So here, if you can see here, so suppose I have a lot of wafers. Here you can see in this figure. If I have the lot of wafers, so what happens if we have the two different lots? From where we need to, so before explaining this thing, let me tell you what the wafer is. Wafer is nothing but it is a substrate on which we have to fabricate the chips. Okay, and might be you have seen the ICs, and there is some silicon substrate on which we have to fabricate the different patterns, different designs, whatever we want. Okay, so that is the wafer. So if the wafer is from different lots, and it is not possible that two different lots have the equal property, so all have the same properties, is not possible. There should be some mismatch in the property of two different lot of wafer. Okay, and if there is some mismatch, so that we call it inter-die variations. Okay, so this comes under the lot to lot one. Second one could be like wafer to wafer. Even though we have the single lot, from same lot, if we have the n number of wafer, n number of slices, so each wafer can work differently. They can act differently. Okay, so if two wafer from a single lot or from the same lot, if they are working differently, then that also comes under the inter-die variations. So we cannot say that if we have a single lot and if we have n number of wafer on that lot, so all the wafers will work equally. Okay, so this is not true. Okay, so this problem we call like inter-die variations. Again, suppose I have a wafer on which I have to fabricate n number of chips. Okay, so this each block what we are seeing here, these are nothing but they are the dia. Okay, each block they are dia. So on a single wafer we can have n number of dias. Okay, and so if I have a wafer, I have n number of dia. So it is not possible that each section of the wafer is uniform. So if each section of the wafer is not uniform, not perfect, in that case, the dia on different section of a same wafer can work or can act differently. Okay, so this we also we call it dia to dia variations, and that also comes under the inter-dia variations. Okay, now the question is where the chip is. So okay, so if I have a dia, so on a single dia I can have the n number of transistors. So whatever blocks you can see here, this is the nothing but this is the single chip. Okay, and this chip and there is n number of chip on a wafer, there is n number of wafer on a lot. Okay, so this is all about the inter-die variations. Now suppose I have a dia. Okay, in a single dia, it is not necessary there will be a single transistor. We can have n number of transistors in a single dia. Whatever chip we have, in a single chip we can have thousands of transistors. Now, if suppose I have two transistors which are identical and I want to fabricate on this dia. Okay, so ideally our assumption is both the device should work equally. The performance of both the devices should be same. But in practical, while fabrication, it is not possible that two devices are ideal and that can work equally. Yes, they can work, but there is some probability that the two devices, even though with the same specification, cannot work equally. Okay, so if there is some mismatch in the device to device, then those kind of process variations are known as inter-die process variations. Okay, so this is the important thing. Now the question is how to analyze this process kernel, how to analyze these process variations. To analyze these process variations, we need to have two things. The first one is like we need to analyze our circuits on the different process corners. And the second thing is we can have the Monte Carlo simulations. Okay, we can run the performance of a single transistor for many times, like let us say 5,000 times. So if I can check a single device for the 5,000 times, and we will try to see which is the point where the performance of device is more concentrated. Okay, so that we can say, okay, this is the mean value, and here is the point where we need to consider, and because the repetition at a certain point is more, so we can say, yes, of course, this device is centered around this particular mean value. Okay, so this is what the use of Monte Carlo simulation. Okay, and that's it. Monte Carlo simulation gives you the center value or the mean value where the performance of this device or the circuit is centered around. Okay? So for that purpose, we need to have the Monte Carlo simulations. Now, the second thing is we can also have a process corner variation analysis, and there we can utilize the different process corners for this particular purpose. And here we can have the 4 different process corners. One could be like the slow process corner. Second one could be fast process corner. Third one could be fast slow. Fourth one could be slow fast, and the last one could be typical one. Now the question is, what is the difference between all these process corners? Okay, so the difference between all these process corner is, let us start with the slow process corners. Why we are calling this process corner slow? So there is an important thing that I think I am expecting most of the audience, they know the fundamental of transistor, MOSFET. Okay, and based on that, I'm just taking this talk. So I'm assuming that if the threshold voltage of transistor is on the higher side, okay, if the threshold voltage of the transistor is on higher side, in that case, delay of the transistor increases. Okay. So what happens while designing a chip, we must have some specification. We must have some power specification. We must have some delay specification, and we must be centered around those specifications, whatever given to us. Okay. So suppose I want to design a chip for, let us assume, for any IoT applications where we need low power, because that IoT node can be placed on the remote locations, and the power supply that we are providing to that node that can sustain for the longer time period. So what we need, our objective should be like we have to design a chip in such a way that it requires less power to operate the chip. Okay, so that the lifetime of the battery can be extended. Okay, so these are some of the and so this is one of the example like IoT nodes. The second example could be like if I want to utilize our chip for the server or high performance applications for the computational units. In that case, our prime objective is like whatever chip we have designed, that should be as fast as possible. Okay, the performance should be faster. Okay, so these two are the extreme cases. One extreme case is the power, and the second case is the delay performance. Okay, so whatever the specification we have, based on that we need to check where is the performance, and that need to be considered. So if our target is like high performance applications, in that case the delay should be as small as possible. And if I have designed a chip, and if I have tested that chip on the slow process corners, where I'm assuming that the devices are very slow, and if even though at slow process corner, if the chip is meeting our specification, whatever it is given, then we can say that it is perfectly fine, it is tested, and that can be used for that application for what we have decided the specifications. Okay, so the slow process corner gives the specification about the speed. What is the limit of the speed? What is the limit of performance? Similarly, if we talk about the fast process corners, where the threshold voltages of both the transistors are on the lower side, in that case, because we have the lower threshold voltage, so the power dissipation will be higher. Leakage power dissipation will be higher. And if the leakage power dissipation is higher, so total power dissipation will also be higher. So on the same set, whatever we have designed, And if it is perfectly working, even though at fast process corner where the power dissipation is more, and if the power consumption is under the limit and it is matching with the specification, so we can say that even though after running at the fast process corner, the chip is perfectly working, and that can be utilized for the purpose for what we have designed the chip. Okay, so the fast process corner is basically utilized to check the power specifications. Okay, and in the normal condition, we generally used to run our chip on the typical where there is a trade-off between the power and the delay. And okay, so these are the, and similarly the slow fast process corners can also be tested, like one of the transistor threshold voltage is higher and another one is a lower one, and vice versa. So that can also be tested. But these three are the very important one, like fast, slow, and the typical one, which gives you the speed specification, power specification, and the typical one is where we are running our chip typically. Okay, on the normal conditions, we used to run our chip on the typical side. Okay, so this is the importance, and this is how we can check the specification with these process corners. Okay, now the second one is so this is all about the global variation or inter-die variations. Now the second kind of variations are like intra-die variations. The first and very important intra-die variation is the oxide thickness variation. What this oxide thickness variation is, how this comes into the picture. So the simple answer of this question is, suppose I am miniaturizing the transistors. Suppose I have a long channel device, bigger device, and if I want to increase the density, chip density, in that case we have to scale down the transistors. Okay, if I am scaling down the transistors, so most of the parameters are also scaled down, whether it is the width or it is length or it is oxide thickness. So the oxide thickness also is going to be reduced. Okay, now the question is where this oxide thickness variation comes into the picture. For example, for the longer channel devices, let us assume the oxide thickness is 10 nanometer. Okay, I'm considering for longer channel devices, the oxide thickness is 10 nanometer, for example. And while oxidation process, there is a tolerance of 1 nanometer. What it means? It means that I'm assuming that the oxide thickness should be 10 nanometer, but throughout the channel, at some places, the oxide thickness could be 9 nanometer or it could be 11 nanometer. So there could be plus minus 1 nanometer tolerance. Okay. Now, so this is the scenario if we have the long channel devices. So here the variation is about 10%. So the tolerance is of 10% is there. Now let us talk about for the short channel devices. If I have scaled down the devices, where let us assume oxide thickness is like 2 nanometer. And if the oxide thickness is 2 nanometer and still during oxidation process, there is a tolerance of 1 nanometer, there is a variation of 1 nanometer. So what it means, if itself our oxide thickness is 2 nanometer, so might be if there is tolerance is same like 1 nanometer, so the thickness could be 1 nanometer to 3 nanometer. So here the variation is around 50% from its original value. Even though there is the same kind of variation of 1 nanometer, but for the lower technology generation, the 50% variation can change the performance or change the property of the devices drastically. So at the lower technology generation, this oxide thickness variation need to be considered. Okay, so this is one of the parameters which is really very important. Second one is the random dopant fluctuation. What happens? What this random dopant fluctuation is? Doping is very important, especially if you are fabricating the chips or designing the devices or fabricating the devices. Okay, for longer channel devices, the number of dopants are very high. Okay, but as we scale down the transistors to maintain the property, to maintain the characteristics, the number of dopants also reduces. Okay, so the example is same. Like suppose I have older technology or long channel devices where number of dopants, let us assume 1000. And if there is some variation of, let us assume 10 dopants. So it could be like 990 to 1010. But if we scale down the technology, for the lower technology, you must have the less number of dopants. So if suppose you have the dopant like 50 only for the scale technology, and if there is some still the fluctuation is like 10 dopants, so it will swing from 40 to 60. And this variation is too much as compared to the long channel devices. So because of this, there is some fluctuation in the performance parameter, and that also need to be considered. So we need to maintain the consistency in the dopants, how many dopants we have. Okay, so this kind of problem is known as the RDF, or random dopant fluctuation. Third, and the very important thing is line edge roughness and the line width roughness. Okay, what this line edge and line width roughness is, ideally we are assuming that whatever the devices we have fabricated, this should be something look like this. Okay, but practically it is not possible. Why it is so? Because up to 130 nanometer, there is no problem, because whatever the light we are using for the lithography process, that the wavelength of that light is 193 nanometer. Okay, so if we have the 193 nanometer wavelength of light for the lithography process, so up to 130 nanometer, that wavelength of light is sufficient, and that can be utilized to fabricate the device perfectly. But even though if we have scaled down the technology lower than 130, like 65, 45, 32, whatever we have, even though the same wavelength of light is used for the lithography process. And here, because there is a mismatch in the wavelength of light in the technology node which we are fabricating, because of this, there is some roughness on the lithography process. Okay, and this roughness is known as line edge roughness. So we were expecting that the pattern should be something like this, but practically what we get some roughness on this side. So there the edges could not be uniform. There is some roughness in the edges. Okay, and similarly the width cannot be uniform. There should be some like here you can see the width is more and here the width is less. Okay, so there is some variation in the width. So this kind of problems can create the this kind of the issues can create the problem in the performances, or they can degrade the performances. If the channel is something like this only, so the device will work perfectly. So whatever we do on the simulation, they are the ideal one. We are considering the ideal one, but practically it is not possible. Once the device is fabricated, might be there is a huge deviation between the simulation work and the experimental work, and this is because of these secondary effects which we are not considering while simulating the designs. Okay, so here we can see, like in this particular section, the line edge roughness and line width both are present, but in third one here you can see the width is uniform throughout the channel. Okay, but the edges are not uniform. So here only line edge roughness is present, but line width roughness is not there, because width is uniform throughout this channel. But here the line width and line edge both are present. So because of this one, the performance of the devices degraded. Okay, so this is all about the process variation. Now let us talk about the supply variation and the temperature variations. If we talk about the gate delay, the gate delay depends on the supply voltage whatever we have used, and the transistor threshold voltage which we have utilized to design that particular circuit. Okay, the important thing to note in this particular slide is, first point is, if the supply voltage is very high, then the delay or the gate delay is going to be reduced. Means the delay is inversely proportional to the supply voltages. Okay, but at the same time, because we have increased the supply voltages, that will lead to higher power dissipation, because there are two types of power. Majorly, there are two types of power dissipation. There are other components as well, but majorly we consider like static power dissipation in the dynamic power dissipation. And if we talk about the static power dissipation depends on the drain current, whatever flowing through the device, and the supply voltage, whatever we have used. And they are directly proportional to the supply voltage. So if I have used higher supply voltages, then the static power dissipation will be higher. Similarly, if you consider the dynamic power dissipation, so dynamic power dissipation, we know that the formula is like alpha FCV square, where alpha is the activity factor, F is the operating frequency, C is the capacitance, and the V square is the supply voltage square. Okay, so if we have the dynamic power in this particular term, so what will happen if we have the higher supply voltage, the dynamic power is also going to be increased with square law model. Like if we have changed a supply voltage with a small amount, that will be squared and the dynamic power dissipation will be increased. Okay, so the important point of consideration in this discussion is, like I just told you, like if we are increasing the supply voltages, then the delay is going to be reduced, and this is perfectly fine if your objective is high performance applications. But on the other hand, at the same time, you have to pay in terms of more power dissipation. So this cannot be considered as energy efficient devices. So to make it energy efficient, there are different way that could be utilized. One of the way, like reduce the supply voltages. So if somehow you can reduce the supply voltages, this dynamic power dissipation and the static power dissipation, which were directly proportional to the supply voltage, that can be reduced, and we can say that that can be used for the energy efficient applications. But the question is, like, then why we cannot reduce this supply voltage with the very small value, so that we can save the power? The important thing is, to operate any chip, we must have certain limit that require a certain supply voltage at which it is giving the optimum delay and optimum power. Okay, if you are keep on decreasing the supply voltages, the delay will increase. Might be it can create a timing failure. Okay, so this is the problem. We cannot reduce the supply voltage directly. It is not just like a scale that move left and right. It's not like that. We have to come up with some optimum value where the power specification should meet, where the delay specification should meet, and if both the parameters are meeting or they are close to each other, then we can fix the supply voltage, and that supply voltage is used to operate that chip perfectly. Okay, and to analyze these things, one of the very important thing that is used, and that parameter is known as power delay product. Okay, so we need to find some optimum value of power and delay product, and at which the PDP is very small or low, the supply voltage will be considered the optimum one. Okay, now as I already told you, so this is all about, so see, if there is a small fluctuation in the supply voltage, might be it can create the problem in the delay, it can create the problem in the power dissipation. So whatever the designs we are designing, that must be resilient to the supply voltage. So it should not vary with the supply. It means the performance should not affect with the variations, small variations. As I already told you, we have the power dissipation formula, like FCV square. So I just talked about what is this F, what is this C, and what is this V. So F is the operating frequency. So if you are increasing the frequency, then the power dissipation will be higher and something like that. There is one more important term in this dynamic power formula, that is the activity factor. Okay, what this activity factor is? Activity factor that decides. So suppose I have a chip. Let me take that figure. Okay, suppose I have this chip. Okay, and in this particular chips, let us assume I have a different model. Let us assume this one the model 1, this is the model 2, this is the model 3, 4, 5, 6, 7, something like that. Might be this first module is for the storage, second module could be like arithmetical unit, third one could be like the logical unit, something like that. So we can have the n number of different modules in a single chip. Ideally, what we are expecting, all the modules should have the equal activity factors. Means all the modules should work equally, but this is not true in practical. Some of the module may have the higher activity factor than the others. So what happens if the activity factor is higher, the dynamic power is going to be increased, and if the dynamic power is going to increase, there is a heat dissipation on that particular module. And if there is heat dissipation on that particular module, this will create a hot spot on a certain region. And if the temperature is changing, that will create problem in the performances. Let me connect all these things again. Suppose I have a chip. I'm assuming that all the modules should work perfectly, equally. So at normal room temperature, at normal conditions, whatever we have provided, the chip should work perfectly. And I'm assuming that the temperature will be constant throughout the operation, the supply voltage will be constant throughout the operation. But in practical, this is not true. Due to this activity factor, some of the region become the hot spot, and the temperature of certain region increases. And if the temperature of certain region increases, then the performance is also degrading. Okay, so here we can see, like, if we are increasing the workload of a particular module, the switching activity will also increase. And if the switching activity is increasing, the power dissipation will also increase. And because of that, the heat will be dissipated on a certain module, and hot spot will be created, and the temperature of that specific module will also increase. Now, after this much of activity, there are certain module where the temperature is low, and some of the module where the temperature is higher. Initially, ideally, what we were expecting that the temperature will be constant throughout the operation. But now, because of this change in the activity factor of each module, some of the modules can have the higher temperature than others. And if it is something like this, the performance is going to be reduced, or it is going to affect the performances. Okay, so the important thing is, like, this temperature variation should also be maintained. Okay, it should not be like any of the devices that should be tolerant to the temperature variations. So this is all about the temperature variation. Now let us try to connect this PVT in terms of the delay. So if there is a less effect of the process variations, in that case, the effect on delay will be smaller, like delay will be less. But if there is more effect of the process variation, then delay can be increased. And for the other things, like if you have the supply voltages and you are using the lower supply voltage, then the delay will be higher, and the vice versa. Similarly, for temperature, if you have the lower temperature, delay will be less, and for higher temperature, delay will be higher. Now, go to the previous slide. If we can recall, some of the module can create the hot spot. And if they can create the hot spot, the temperature of that module is going to increase. And if the temperature of that module is increased, what it means, the delay is also going to increase, means the performance is degrading. Okay, so if the performance is degrading, might be we will get more delay and we will not get the results as per the expectation. So this is the problem with the PVT variation. So we need to design certain things that need to be tolerant to these PVT variations. But the funny thing is, the problem which we are saying here, like the process variation in terms of reliability, this process variation, this uncertainty, this mismatch can be utilized as a security primitives. How it can be utilized, I will tell you. Okay, yeah, this question, keep this question unanswered. I will answer this question when I will talk about the security. Okay. Now, I was also discussing about some reliability concerns, like time-dependent reliability concerns. So one of the reliability concern, time-dependent reliability concern, is the bias temperature instability. What this is? So what happens? BTI is nothing but it is a time-dependent phenomena, and this is due to the dangling bond defects at Si-SiO2 interface. Now the question is what this dangling bond is and from where it comes. Okay, so let me explain this particular thing. Initially, whatever we have, like we have the silicon substrate. On this silicon substrate, because if I want to create the MOS structure, where we need metal, oxide, and semiconductor, metal for the gate terminal, oxide for this oxide layer, and the semiconductor for the bulk one. Okay, so if I want to create the MOS structure, in that case, I have the silicon substrate that will act as a semiconductor. On top of it, what I need to do, I need to oxidize it. Okay, so there are two ways for the oxidation process. Okay, so because if I want to create SiO2, if I have to create this SiO2 on top of the Si or on the silicon, so what I need to do, I need to oxidize it. Okay, so this oxidation process can be of two types. Either it could be wet oxidation, or it could be dry oxidation. But for the lower technology generation, the wet oxidation is preferred one, and because that is giving the better performance as compared to the dry one. Now, if I am using the wet one, then there is some involvement of the H2O. Okay, so if there is some involvement of H2O, so that oxygen can make the bonding with the silicon, and that will create the SiO2. Okay, this is really very easy. Okay, so SiO2 can be made, but because in H2O there is some hydrogen component as well. Okay, hydrogen atom is there, so some of the hydrogen atom, they can be bounded with the silicon, because SiO2 is the strongly bonded, and that will create the SiO2 layer. But there is some loosely bond with silicon and the hydrogen, that this hydrogen comes from the H2O, and this hydrogen, this bond, SiH bond, is the dangling bond, and the bonding and the strength of this is very small, very less. With the small energy, this bond can be break, and they can tunnel into the oxide, and if they can tunnel into the oxide, they will change the property of those oxides, and that is the problem. Okay, so this SiH bonds can create the problem, and from where this BTI effect comes into the picture. Okay, so basically this BTI increases the threshold voltage and affect both NMOS and PMOS transistors. And basically there are two types of the BTI. The first one is the negative BTI, and the second one is the positive BTI. Okay, so so here we can have the NBTI and the PBTI, and that can be observed in both kind of devices, either it is the PMOS or it is the NMOS one. Now the important thing is, whatever here we can have the four different components. One component could be like NBTI in the PMOS transistor. Second component could be like NBTI in the NMOS transistor, PBTI in the PMOS, and the PBTI in NMOS. So we can have the four possible combinations. But out of all these four combinations, this NBTI in the PMOS transistor is more sizable and more dominating component as compared to others. So generally researchers consider NBTI in the PMOS transistors. Okay, so this is the thing which we need to consider, and this becomes especially a prime concern, especially if the oxide thickness is less than 2 nanometer. Okay, so because the NBTI is the dominating component, so let us talk about the NBTI in detail, how this affects the performance, and how this can be clubbed with the security features. Okay, so here this NBTI is mainly due to the negative gate to supply voltage, and the second reason could be like elevated temperature. Elevated means higher temperature. Okay, so because here let me just directly take this example. Negative gate to supply voltage means what? If the gate terminal of the transistor is connected to the ground terminal, and if the source terminal is connected to the VDD, so if you see here, the VG minus VS will give you minus VDD. Okay, so if I want to calculate VGS, so VGS is nothing but VG minus VS, and VG is 0 volt and VS is VDD, so that will give effectively VGS is equal to minus VDD. And if the potential difference between gate and source is minus VDD, in that case, stress effects comes into the picture. Okay, so if the NVTI stress is in process, in that case, the loosely bond, like the dangling bond, they break and they can tunnel into the oxide, and effectively they increase the threshold voltage. Okay, so this is the problem. Like whatever the bonding is there at the interface of Si and SiO2, this loosely bond, they start breaking and they can turn into the oxide one. Okay, and because of this, threshold voltage is going to increase. But one very important thing about the NBTI is this trapping can be recovered back. Okay, so the second phase is NBTI recovery. NBTI recovery can happen if we change the polarity of gate and source one. Okay, so if I have changed the gate to VDD and the source to grounded, in that case, NBTI recovery phenomena will happen. Okay, in that case, whatever the charges are trapped into the oxide, they can recover back. But the very important thing is 100% charges cannot be recovered. Okay, so there is some permanent trap that cannot be recovered, and effectively it increases the threshold voltage. Okay, so this is how the recovery works. NBTI is basically divided into two things. Yeah, I think this is not that much related to the security, so I'm just skipping few things, and I will directly connect to the security side. Yeah, so before going into this, there are two types of the NBTIs. The first one could be like static NBTI. Second one is the dynamic NBTI. Static NBTI means if there is no condition of recovery, there is always a stress. Those kind of NBTIs are known as the static NBTI effects. But if the stress and recovery, both phenomena is happening at the same time or simultaneously, in that case, we call it the dynamic NBTI. Because in the dynamic NBTI, stress and recovery both is happening. So we can say that we have some stress, then we are recovering, then stress, then recovery. What it means, the effective, the effect of this dynamic NBTI is somewhat lower than this static NBTI. Okay, so this is how we can observe. Like there is some stress. This is the stress one, then recovery, but 100% cannot be recovered. I just told you there is some permanent shift. Stress and recovery, stress recovery, and effectively the threshold voltage is increases to certain limit that can lead to the timing failure. Okay? So this is the problem which can create the problem in the timing failure. Okay. This particular graph slide, this represent like what are the different parameters that decides at what time the device is going to be failed. Okay, so that depends on many parameters. First parameter is what is the supply voltage we have used, what is the stress voltage we have used, whatever the time for we have operated the device, what is the temperature at which we have operated, and what is this oxide thickness. This is also very important, and what is the defect density of each devices. Okay, so these are the many things. Like if the oxide thickness is less, then the breakdown will be early. Okay, if oxide thickness is higher, then the breakdown will be late. So what it means? It means that if we have the short channel devices and the long channel devices, so in case of short channel devices, breakdown will be early with all the conditions. Okay, so these all are the conditions. Like if you will increase the supply voltage, definitely there will be more effect of the NBTI. Okay, so for the lower supply voltage, effect of NBTI will be less. Okay, but at the same time, because see, now one may ask, like if we can reduce the voltage, then the effect of NBTI can be reduced. Okay, yes, I completely agree with this. But at the same time, we know that if we are reducing the supply voltage, then the delay of that circuit is also going to increase. And if delay is increasing, the performance is also going to reduce. So there is a trade-off. Like we cannot reduce the supply to the certain limit so that we can remove these NBTI effects. We have to keep some supply voltage. So if we have some supply voltage, that will that will give you some NVTI effects. So this is the importance of all the parameters in the NVTI effects. Now this slide is going to be very interesting. Okay, so I will tell you something about the NVTI effects. So one more important thing is like the VTS shift increases by approximately 4% for each new technology generation. What does it mean? It means that, suppose, let us currently I am considering 45 nanometer technology, and for example, after 1 year of stress, the threshold voltage is changed by, let us assume, 10%. Okay, after 1 year of stress, whatever the original value was, the threshold voltage has been increased by 10%. But if you are considering the next technology, like initially I was considering 45, then if I go to the 32 nanometer technology generation, in that case, the threshold voltage shift or threshold voltage change will be increased by 4%. Initially it was 10, now it will become 14%. So for the lower technology generation, the effect of NVTI is severe. It is problematic. That can create the timing failure, timing error. Okay, so the important thing is, like for the SCALE technology, the NVTI becomes the serious concern that need to be considered. And someone may ask, if I have the NVTI effect in the devices, what are the effects we will observe? So here are the effects of NVTI. The first one is, I have already told you, the threshold voltage of the PMOS transistor increases. Now let us try to correlate few things. First and very important thing is, I have already told you, if the threshold voltage of transistor is increasing, then the leakage current will reduce and the delay will increase. Okay, so the two phenomena, like second one is, if the threshold voltage increases, then the drain current will reduce and the speed will degrade. Okay, so it means the delay will increase. So if I am considering the NVTI, in that case, if the speed is degrading, so this is the serious, really a problem. Like the speed should not degrade. Okay, so the NVTI looks like a problem. Okay, let me say it again. What I'm saying, this is really very important thing, and might be you will be happy to hear like NVTI is something like funny thing. Okay, so the first thing, like as I already told you, the effect of NVTI is like it is increasing the threshold voltage of the transistor, and if the threshold voltage of transistor is increasing, the delay is going to increase. So this is the problem. Okay, so for any designer who is considering the high performance applications, this NVTI is really a problem. Okay, it should not be, means NVTI should not be present in the circuit. But if I go to the second point, my conclusion get changed. Right? Whatever I thought it is going to be changed. It says that the degradation in the drain current means the current is going to be reduced, and we know that current and the power dissipations are related to each other. If the current is reducing, the power dissipation or static power dissipation is going to reduce. Okay, so if there is some effect of NVTI in a circuit, then the power dissipation is going to reduce. Now the important thing is, if your target is the energy efficiency, so this NVTI will further reduce the power dissipation because the drain current is going to reduce. So the energy efficiency, in case of energy efficiency, this NVTI seems it is a benefit. Okay, so now this is an important thing. Like if your objective is the energy efficiency, NVTI can be considered as a benefit. But in terms of these high performance application, NVTI is a problem. So based on the application, you can decide whether NVTI is a problem or NVTI is a benefit. Now, the important thing is how we can relate this NVTI for the security applications. Now, I'm just briefly explaining. Details I will explain in the later slides. Okay. Now the important thing is, like, suppose I have a chip, I have a PC, I am using this PC for a longer time period. Okay. If there is some NBTI effect, I just told you there are two types of the recovery. There are one is like there is a permanent shift. So 100% trapped charges cannot be recovered. So whatever the shift in the threshold voltage is there, the permanent shift cannot be reduced. Okay. So for example, I have a electronic gadget, I have a chip, and I have used that electronic gadget for, let us assume, 3 years. Even after 3 years, might be the system get failed, but in that system, some of the chips are good. They are not failed. So what people do? They used to take out those chips, those ICs from the junk of electronic chips and electronic boards, and then what they do? They used to remark it and they can resell it. So this is the security threat. This is the security problem. Let me reconnect it again. Suppose I have a chip, I have a electronic system, and that electronic system gets failed after 3 years. But whatever the chip we have used, that chip may have faced the NBTI effects. And due to this NBTI effect, there is a permanent change in the threshold voltage of the devices. So after 3 years, and the new IC and this 3-year-old IC, it is not necessary these two IC will perform equally. They may have a different current flow, they may have a different power dissipation, they may have a different delay. Okay, so what people used to do, like they used to take this electronic junk, they used to take out the working ICs and they resell it in the market. They remark it and resell it. This kind of phenomena is known as counterfeit electronic. I will tell you in the details. So this kind of problem is counterfeit electronic, right? So what they do, they are reselling, and again the older IC comes like a new IC in the market, and this is the security threat. So now the question is how this NBTI can be utilized to detect those ICs. So let me tell you how we can do that. Because I just told you, due to this NBTI, the leakage current is going to reduce and the speed is going to reduce. Suppose I have one old IC with the same number, I have a new IC with the same number. Okay, like suppose I have purchased one IC from the market, they are claiming it is new, but it is old one, which is the recycled one. Okay, so what I will do, I will test the standby leakage current, because there is a permanent shift in the threshold voltage of the devices, so that there is some change in the current even though I have not operated it. So there is definitely there will be some change in the current in the old IC and in the new IC. And if there is some change in the current, we can compare these two currents which is flowing through both the ICs, and if there is some mismatch in the current, then we can say that this IC which you are claiming that this is the new one is not new, this is the fake one, this is the counterfeited one. Okay, so this NBTI is a problem, especially if you are considering the reliability concern. But at this point of time, where the problem of recycled IC is increasing day by day, this NBTI gives you the hope and some idea to detect those recycled ICs, and the security can be improved. Okay, and this kind of things are known as counterfeit electronics and detection techniques. Okay, so this is how we can relate this problem, reliability issue, with the benefit if our target is the hardware security. Okay, so yeah, definitely, just like I took the example, like we can consider this drain current. We can also consider the delay of the some of the module in the chip, old chip and the new chip, and the delay will also be changed, and that can be compared, and we can judge whether the things we are claiming like this is new IC is not new. Okay, so this is how we can get benefit of this problem in case of the security. I think I missed one thing, like when I was discussing about the process variations. So how that process variation can be utilized as a benefit. So that question is answered. So I will answer that question in few slides. Okay. Here is the things like here we can see with the different stress time. If I am increasing the stress time, the threshold voltage is going to increase, and the standby leakage current is going to reduce. Okay. So this is the important thing that need to be considered. This is the same what we have. Here is very important thing. What I just told you, like the effect of NBTI is increases with scaling down the technologies. Like initially, if you had a 130 nanometer, and then if you are scaling down to 32, then the delay is going to reduce, the leakage power is going to increase. But the effect of NBTI, if you see, the threshold voltage shift is increasing with respect to the scaling down the technology from 130 nanometer to 32 nanometer, and similarly the delay shift due to this NBTI is also going to increase. So this can be utilized, like for the lower technology generation, the effect of NBTI is very high, and if it is high, then that need to be addressed and that need to be considered. Okay, so yes, one more important thing I just wanted to consider here is, like, suppose I have a chip which is fabricated with the older technology, and there is another chip which is fabricated with the latest technology. Okay, I just told you the effect of NBTI in the older technology is less as compared to the newer one. Okay, so if someone is doing counterfeiting electronic, like someone is reselling or remarking or the IC which is fabricated with the older one, so there is a quite difficult to detect those ICs which are fabricated with the older technology, because the effect of NBTI is very less, and effect is very less, so we cannot use this NBTI technique to detect those ICs. We need to have some different kind of testing technique. Okay, but for the lower one, that simple NBTI testing can act as a tester, and we can test it. So this NBTI can be benefit, especially for detecting the counterfeit electronic at the lower technology generations. Okay, so this is an important thing that I need to consider. Now, other than this negative bias temperature instability, so I have finished only 15 slides, and I have 35 minutes of time, right? So I need to cover it as soon as possible. Okay, so this is all about the NBTI. Now let us talk about the hot carrier injection. The hot carrier injection is mainly due to the the effect of HCI and the BTI is almost same, but the phenomena is different. Okay, in BTI, if we see, there is a trapping of charge carriers, but in HCI, what happens? Some of the electrons get accelerated, they get higher sufficient kinetic energy, and they start trapping. So if they have the sufficient kinetic energy, they can trap into the oxide. And if they can trap into the oxide, they will increase the threshold voltage. And if they can increase the threshold voltage, the performance of the devices will be changed. Okay, so see, the effect is same, like change in the threshold voltage, but the phenomena is different. Okay, and the hot carrier injection is mainly occurred during the switching of the logic, but BTI is happening during any particular state. Like if it is in stress condition, then the NBTI effect will come. Otherwise, there will be no stress conditions. There could be some recovery states. Okay, so this is all about the hot carrier injection. That increase these things. Now the important thing is like time dependent dielectric breakdown. That this is really an important thing that need to be considered. What happens if I have a MOS structure? I have a silicon, then oxide, then the metal one. Okay, each dielectric material, like this SiO2 is nothing but that is the dielectric one. Each dielectric material have their strength, electric field strength, how much electric field it can sustain. Okay, but what happens if we know that if we keep on increasing the electric field across the terminal of the dielectric material, might be that dielectric material can lose its property, and it can act as a conducting material. Let me say it again. Suppose I have a dielectric material, I have applied some potential, I have applied some electric field across it, and if I have some minimum electric field, then that material will completely act as a dielectric material. But if we are increasing the electric field across this dielectric material, after a certain time period, after a certain limit, that dielectric material can start losing its property, and this can act as a conducting material. Means it can, so this kind of the breakdown from dielectric to conducting is known as hard breakdown. Okay, so this kind of the breakdown is known as hard breakdown. But this is the phenomena in the dielectric one. But in reality, if we are talking about the semiconductor devices, in those semiconductor devices, what happens if we are operating a device for the longer time period? So there could be, like, initially we have the silicon, SiO2, and there is some polysilicon like gate. Okay, so there is some minor defects inside the oxide one. Okay, so with respect to time, number of defects are keep on increasing. And if the number of defects are keep on increasing, after a certain time, there may be, like, it may create a leaky path between polysilicon and the silicon. And if there is some leaky path between polysilicon and the silicon, that will create a problem, like it can break down. So because this breakdown is coming with respect to time, like with respect to time, this micro leaky is increasing. So that is why we call them time dependent dielectric breakdown, because this dielectric material loses its property because through this dielectric material there is some flow of current. So that is why we call them time dependent dielectric breakdown. Okay, so this is also one of the serious concern, reliability concern, especially if we are targeting the reliable system designs. Now this is a very important thing. So suppose I was just discussing about the NBTI, PBTI, SCI, and TDDB. These all kind of phenomena are at the physical level, whatever the devices we have designed. But if we talk about the device level, the same phenomena can affect differently at the transistor level. Like if I have the devices, then it can change the threshold voltage of the devices due to this NBTI, PBTI, SCI. It can change the transconductance of the devices, or it can change the current flowing through the devices. So even though the phenomena is same, which is at the physical level, but that can affect differently at the device level in terms of threshold voltage shift, transconductance shift, and the drain current shift. Similarly, if you go to some higher abstraction level, like gate level, by using these devices, so let us assume we have the inverter. So in this inverter, I will not talk about the threshold voltage. The same kind of phenomena that can affect in terms of delay. So I will consider this delay, how the delay is going to change with respect to this NBTI. Even though phenomena is at the physical side, but that will reflect in terms of delay change, in terms of power change, if I am targeting the power gate level. Okay. Similarly, if we further increase the abstraction to the circuit level, then what we do, let us assume the SRAM design, which we have connected back to inverters. In that case, even though we have the same phenomena at the device physics level, but we need to analyze in terms of static noise margin in the critical charges. Okay, and similarly for the system level, even though phenomena is at the physical side, but that can affect in terms of timing violation in the data corruption. So the key point of consideration in this slide is, like, even though there is a defect, there is a problem in the during at the physical level, but they act differently. Different parameters are reflected at the different abstraction level. Okay, so we need to decide at which abstraction level we want to consider, but at each abstraction level, the different parameter we need to analyze. Okay, so this is how we can compare these things. This is the Bar-Stuff curve. Yeah, this is, I think, I don't want to spend too much time because this is purely related to the reliability one. So I just wanted to cover a few things on security side as well, because we have the limited time. So yeah, let me quickly go through it. I don't want to skip any other slide. So this Bar-Stuff curve especially shows, like, if once the chip is fabricated, initially there may be failure after the chip has been fabricated. So those kind of failure are known as the infant mortality. Okay, and once the chip is fine, then the failure rate reduces because they are started working perfectly fine for certain period of time, and this time period is like known as the early time. But once the chip is in operational, then they will keep on operating. But with respect to time, the failure rate is increasing due to these defects what we discussed in the previous slides. And after a certain period of time, those chips can be wear out and they can fail. Okay, so this limit, whatever we can observe here, is the operational limit or on service limit, and others are like wear out limit and other things. So this is what about the bathtub curve. It looks like a bathtub. That is why this bathtub curve is we call it bathtub curve. This is especially very important if your concern is the reliability, because our concern is the security. So I'm not focusing on it. So I'm skipping these things. Maybe in case time permits at the end, I will discuss these things in detail, because this is really very important to understand how the phenomena, different failure phenomena can change the behavior of the devices and the circuits, subsequently circuits. So yeah, I will try to cover it later if time permits. Now let us talk about, yeah, so other than these things, there is one more mechanisms like the soft error mechanisms. I have already told you, if we have a semiconductor devices and if there is some probability of high energy particles on it, so this high energy particle strikes on the bulk of the semiconductor material, and they can create a secondary electron hole pairs, and these secondary electron hole pairs are collected at the drain side of the devices or the sensitive region of the devices. And because of that, it creates some glitch at the output, and this glitch can change the static logic. Okay, so here you can see these kind of things we can observe. Basically, if you want to check the performances, what we need to do, because I have already told you, this looks like a double exponential current pulse. So to test in any of the circuit, either we can apply in the negative direction or in the positive direction. That completely depends on what kind of logic state we have. If at the output side we have the logic high, in that case we need to connect this negative direction current pulse, and vice versa. Okay, so what it do, if I have connected some negative current over here, so that will shrink the sorry, that will shrink the charges which is stored at this one, and there is some temporary flipping of logic from 1 to 0. And if there is some storage node connected over here, might be storage node can also be flipped. So this is also one serious concern, and that need to be considered. So in the simulation model, people generally use double exponential current model to explain this one. So here this is the expression for the current which we have injected at the sensitive node, which is the drain of this one, and that is defined with the I peak ET upon TFT fall and T rise. Like here we can see fall time and the rise time and the time constant and other things. Okay, and I peak is nothing but is the peak value of this current. So this is how we can analyze with this one. Okay, I think I need to skip this. This is not that much important. Now, the important thing, let us talk about the security classification. So, till now, we discussed about some of the reliability concerns that need to be considered. And I also tried to connect some of the reliability concerns with the security, especially NBTI. Yeah, I missed the PVT process variation. So now I will cover the process variation, utilization of process variation in the security applications. Okay, so here, so basically, if you talk about the hardware security, basically this hardware security is classified into two categories. Either it could be at the package level, or it could be at the chip level. Okay, so if we are talking about at the packaging, it could be like anti-tamper. Okay, anti-tamper, anti-authentication, anti-tampering plus authentication. We can combine these two things. If you're talking about at the chip level, it could be like anti-tamper, authentication. So in these categories, we can have the different things, like we can utilize like fuses, change of the element characteristics and other things. So let me quickly tell you one by one how we can resolve how we can protect the IC with all these phenomena. So whatever the things we have written in the bottom boxes, these are the protection mechanisms. So one protection mechanism at the chip level, if I'm considering the anti-tamper, so that could be the fuses. Okay, so the fuses can be like we can have we can protect our fuses whatever we are using, and by this it cannot be tampered. We can make it stronger, so we can secure it. Similarly, the important thing I'm just considering, like the physically unclonable function. Okay, so the physically unclonable function is nothing but these physically unclonable functions are used to authenticate the chip, and each chip has the unique challenge and responses. Each puff has the unique challenge and responses, and it cannot be matched with the other one. Okay, and if we have this kind of property, and if the two different designs, two different chips have the different challenge and responses, even though we have fabricated both the chips at the same time, so that cannot be tracked. Okay, so the challenge and responses are used to authenticate the chip. Okay, because let me say it again. I will tell you in the detail how this puff can be utilized. Okay, so the puff is nothing but this is the physically unclonable function that is used to authenticate the chip. Okay, so even though I have two chips fabricated at the same time, but both the chips can have the different process variations. Okay, if both the chips has different process variations, so if there is mismatch in the property, and if there is mismatch in the property, even though both the chips are identical, but the property of the chip will not be identical because of this process variations. So the question which was unanswered when I was discussing the process variation will be answered here. So let me recall the process variation first, then I will tell you how that process variation can be utilized for the physically unclonable function, which cannot be cloned, and that can be utilized for the authentication process. Okay, so see, I was saying like there was a process variation on wafer to wafer, lot to lot, dia to dia, or device to device. So there was a different set of process variations. Okay, suppose I have fabricated two different chips on a same wafer. Ideally, I'm assuming that both the chips would work identical because the designs, parameters, everything are same. But due to process parameter mismatch during the fabrication process, even though we have decided that both the chips are same, but in reality, both the chips will act differently. Both the chips will work differently. And if both the chips are working differently, means whatever the input we will provide, that we call it challenges, the responses will be different. Okay, so the process variation was the problem in the reliability concern, but that problem can be utilized to make your chip unique, because each dia can have the different variations, and the variation cannot be same in all the dia. And if the variations are different, even though the wafer was same, then you can say each chip, whatever we have fabricated on a wafer, that will have the unique property, and that we call it uniqueness. Okay, and if all the chips has unique property, then whoever has designed this chip know the challenge and responses, and the only authentic person can know what is the challenge and responses. So unauthorized person cannot know what the response is, even though they have the same set of chip, same kind of chip, but because both chips will work differently, so each chip will have the different phenomena, different challenge and responses. And if there is some different challenge and responses, then only authentic person or they can identify whether the chip whatever I have received is authentic or not, or the user who is using this one is authorized one or not. Okay, so this is what we call the physically unclonable function. Okay, so the other things like we can also consider this aging. So aging, I just told you how this aging effect can be utilized to counterfeit the electronics. So I have already explained these things. Okay, but in detail, I will try to look into this. Still, I have 17 minutes. Okay, so yeah, so let's try one by one all these hardware security primitives. First one is the like physically unclonable function. Okay, I just explained briefly, but in detail, I will tell you what this physically unclonable function is and how we can improve the security if we have the physically unclonable function. Second one could be like true random number generator. Third one could be like counterfeit electronics, which I have discussed somehow. And the fourth one could be hardware Trojan. Okay, so let us discuss one by one. The first one is the physically unclonable function. Okay, so what happens with the development of various hardware hacking methods, such as side channel effects, use of machine learning algorithm, making the whatever the data we have stored that is vulnerable to the attacker. So to protect all these things, the physically unclonable function is very important, and that gives you a promising solution. Okay, so whatever the problems we have that can be attacked from the side channel attacks kind of things, that can be protected by this physically unclonable function. Okay, so what this PUF do? PUF generates a unique and reliable and the secure key, not only for the cryptography applications, but for the hardware authentication purpose. So this physically unclonable function, they generate a secret key, and this is different for each chip. So only authentic person can know what is that authentication key is. Okay, so if this PUF generate the and that is utilized to authenticate the hardware whatever used, and this is also used for the cryptography applications because we have the unique key. If we have the unique key, so that can be utilized for the cryptography applications. So this is what the physically unclonable function is important. Now let us talk about what is the physics behind this one. I was briefing about the initially, like the physically unclonable function utilizes the process variation problem. So the process variation is this concern if our objective is the reliability. Okay, but if our objective is security, the same process variation, which was the problem for the reliabilities, that can be utilized as a benefit for the circuit designs. So if there is more randomness, because see, the process variations are random. We cannot predict how much process variation will be in a particular chip. So if the process variation is random, it cannot be predicted. So the challenges, whatever I am giving and whatever the responses I am getting out of the chip, that can also be the unique. So for the different chips, that will be unique. So here the process variation kind of problem can be used as a benefit in the hardware security applications. So here we have, suppose I have some authentic ICs. I have some fixed set of challenges. A challenge is nothing but this is the input and the output. So challenge means input, response means output. So if I'm passing some input through the physically unclonable function, it will give some responses, some output. Okay, and if it is the authentic puff, if there is some unauthentic puff, like if someone has come up with the same kind of circuit but they are not authentic, in that case the challenge response pair will not be same. Here whatever the challenge I have given, this mess of challenge I have given, challenge is nothing but its input, and this is a response I have received. If this IC is not authentic, then even though I have the same challenges, I will not get the same responses. Okay, so if the responses are mismatching, then we can check, yes, this is not the authentic IC, this is the unauthentic IC. Okay, so the authenticity of the IC can be checked with this challenge and response pair. So if I have the authentic ICs and I have sent this one to some places, then whatever I have to check it whether whatever the, suppose I have sent some IC from here and then someone has received at some other places. So is there, they have changed that IC or not? Whether whatever IC, whichever IC I have sent from here, it is same or not. So to authenticate that, what I need to do, because the authentic person knows the challenge and response pairs. So what I need to do, again at the response means the receiver end, we need to again check the challenge and responses. And if the challenge response pairs are matching with each other, we can say that yes, this IC is authentic. And this is the same what we have sent. Otherwise, we can say if the challenge response pairs are not matching, then we can say this is not authentic IC. Okay, so this is how we can secure our hardware by using unauthentic IC or untrusted ICs. Okay, so this is the importance of physically unclonable function that generates some secret key, and the secret key is nothing but this is the challenge response pair. Okay. So this is all about the physically unclonable function. So here the important thing which I have discussed about, like here I tried to connect the process variability, which was the part of the reliability, to authenticate the IC. So here we can utilize the reliability issues with the hardware security applications. Okay. Now, so this is all about the physically unclonable function. Now let us talk about the true random number generators. What these true random number generators are. So see, suppose I have to secure the data. Okay, so data security is one of the main concern in the effective and meaningful development of the IoTs and other devices. Okay, if I want to implement it at the larger scale. So this is really very important. So to secure the sensitive data, whatever we have at the sensitive nodes or the IoT devices, the cryptography is one of the solutions that can be utilized to secure the data, whatever we have at the IoT nodes. Okay, and for that purpose, we need some random key for the encryption and the decryption. So if I am doing cryptography, so for that purpose, we need to have some two processes there, encryption and the decryption. Okay, and to encrypt, we must need some random number key that can be used to encrypt the data, whatever we have, that cannot be predicted. Okay, so for that purpose, true random number generator is important. So true random number generator is utilized to generate the truly random number that can be used to encrypt the data, whatever we have at the sensitive nodes. Okay, so this is the importance of true random number generator. But the important thing is how we can generate the truly actual true random numbers. Now, the one very important funny things comes into the picture here. The noise effect, which is not required, especially if I'm talking about the reliability. So if I have a chip, I have a circuit. So the interference noises should not be present inside in the chip. So effect of noises should not be there. So if my concern is the reliability, in that case, the noise should be as small as possible. And this is the prime concern, especially if I am designing the reliability side, if I am designing the circuit considering the reliability. But the problem which was like noise, which we call like white noise and something like flicker noise and this kind of noises, those noises can be utilized as a benefit so that we can have the more randomness of the number, whatever we are generating. Okay, so my key point of consideration here is like this noise was the problem if we are considering the reliability, but the same noise can be utilized to generate a truly random number. So here, so like if I have some random number which is generated, so if it is truly random, so we can have like this is required for the secrecy and the privacy. But if it is not true, if it can be predictable, in that case, the hacker can see like some of the patterns are repeating after a certain period of time. So some hacker can see like, yes, this pattern, if you can see here, this pattern is coming after this particular time period. So they can predict like, okay, this may be the key to open the, to access the data. So that can be attacked, that can be predicted. So if the key which we have generated is truly random, then it cannot be predicted. So here the noise is important. The external noise is random telegraph noises are very important, especially to have a truly random number. Okay, so these things need to be considered. So this is all about the true random number generator and importance of the reliability concern to implement or to design the truly random number generator. The third one could be like the counterfeit electronics. I have already discussed these things. But suppose I am the end user. I have some e-waste. I have thrown it in on the garbage. Might be someone can process that e-waste and they can again send it in the global market. Okay, and then again we can use it. Okay, so this is really a serious problem nowadays. Okay, and then to overcome these things, I have told you one of the concept like the reliability issue, which is the NBTI, that can be utilized to detect the counterfeit ICs. Okay, so whatever recycled ICs we have, that can be detected by the NBTI. But the question is, like, what are the different sections at which there is a chances where we can have the counterfeit? Okay, so where where we can have like, so during the design time, there could be some counterfeiting, like they can clone the design, whatever design we have, they can clone and they can reuse it unauthorized. An unauthorized person can design it and they can use it. So this is also one of the problem during the design. They can tamper the design, whatever they have. So whatever the design I have made, might be it can be tampered, and that is fabricated, and might be this could be the problem. Okay, so at the different stages of the supply chain, there could be the different things. During fabrication, might be they have overproduced the chip. Let us assume they have the contract of to fabricate 1 million chips, but they have fabricated 1.1 million. So 0.1 million chips can be resell without any authentication. So this is also one of the problem. During the assembly, there could be problem like they can overproduce, they can create some defect, they can tamper the assembling and other things. So there is some problem of the counterfeiting. During distribution, they can, like, suppose I have 1 million the original chips, and now what they do during distribution, they have added some of the counterfeited IC, some of the recycled IC here. Okay, so that will be sold as a new IC. So this is also one of the problem where the component this component can be added. During lifetime, they can be recycled, they can tamper and other things. And so these are the different stages where this electronics component have the concern during this supply chain, and that definitely need to be addressed. Okay, and to address this counterfeit IC, I have just told you one of the key term, that is the BTI effect, that can be utilized to detect the recycled IC. Okay, and this is really a very important thing to work on. Another thing is like hardware trojan. Hardware trojan is nothing but if a small section of the additional or unauthorized things has been inserted into the design. So this is the trojan. Okay, so like I have the idea, I have the trusted idea, like I have the idea and I'm trusting on it, right? So might be I have intentionally changed the specification during the specification design. So this is the part of the trojan. They have done some mistake here. They have done some changes. Might be because of this change, the output IC may work differently. There could be some like tampering file in the HDL side as well. At the IP core, whatever the IP core we have, they can use like malicious IP cores. So that is also one of the problem. During synthesis, mapping, and the placing, they can use the manipulated tool, which will not give you the optimum placing in the routing. This is also one of the Trojan part. So that need to be considered. So there are like, see, hardware Trojan can be inserted at any of the stages during the fabrication process. It starts from the idea to the fabrication. Okay, and this really need to be taken care. Like This is really important to pass all these states through the authentic persons only. If we have sent some design through the unauthentic person, you don't know who are dealing with those components or those blocks. Might be there could be some trojan that can be inserted into it, and they can track the data whatever is stored here. Okay, let me take the example. Like suppose I just wanted to fabricate this kind of chip. So, but while fabricating, they have made some break in the wires. Some of the wires has been breakdowns. They have added some extra wire in between two nodes. So this is also one of the part of the hardware trojan. So these all things can be detected. This must be detected to authenticate the chips. So this is the really serious problem, especially if I'm considering the hardware trojan. Okay, so this was all about the hardware primitives. Now let's talk about some research challenges. So basically, the research challenges are divided into two categories, or based on their time frames. The first one is the near-term reliability issues between 15 to 2022, and the second one is the long-term reliability issues that will come in the future from 23 to 2030. Okay, so these are some of the reliability issues that need to be addressed. So if you consider the near-term reliability issue that is needed to be considered is like TDDV, NBTI, SCI, RTN, and other things in the scale and non-planar devices. So these are the real term where the people can work, they can model them, they can design their circuit by considering these are the phenomena, and they can work on it. The people can also, if they are currently working on the reliability side, they can also work on the gate to contact breakdown. So there's a chances of breakdown of gate to contact. So they can work on this, and they can try to overcome these issues nowadays. The important thing is like till now the models are mature for the planar devices, but for non-planar devices the models are not that much mature. So that can also be considered, especially in the reliability side. Okay, one of the things like 3D interconnects reliability challenges is also one of the concerns that need to be addressed, because as of now the device reliability is too much mature, but the circuit level reliability, system level reliability, this also need to be taken care, and we need to be understand the things. So these all are some of the near-term reliability issues. Yes, of course, some of the embedded, if I'm designing the embedded electronics, I need to consider the reliability of the devices for the critical applications like medical, automotive, and here and there. Okay, so these are some of the reliability concerns that need to be considered in the near future. If I'm talking about a long-term reliability issues, which is coming to be need to be addressed in the future, and the first and the very important thing is like till now the people have considered the device level reliability, but the material which we are going to use to fabricate the device is also very important. So the material level reliability is also one of the future research dimension where the people can consider. Okay, so this is one of the thing. The second one is like as of now the people are considering the device level reliability, but that need to be shifted towards that will shift towards the system level reliability as well, because the effect of these reliabilities are not that much on the system level, but in the near future this reliability concern will affect the systems as well. Okay, and the muon induced soft error rate is also very important, that need to be considered. Muon is nothing but this is the charge is just like an electron, but the mass is higher than the electron, and because of those things, if they are present in the environment, they can create the problem of soft error, right? And that also need to be considered. So these are the few research domain that need to be, they are coming in the near future, and you have to understand the intensity of this one, and you have to focus on this so that you can work on the current trends. Okay, so this was all about the reliability side. In case of any problem like associated with any of the things you want to get some information related to it, definitely you can write back to me, and I will be happy to answer your questions. If we consider the here some funny things comes into the picture. Like if I'm talking about the can I take 2 more minutes, right? So I have one more slide and I will finish it up. So if I'm considering security reliability challenges, uh, on the left side, we have the table like process variation, noise, temperature, supply, aging effect, radiation effect. All these are the reliability concerns. Okay, but if I have to design some logic circuits, in that case, the process variation is a problem. In all other kind of problem, these things are the problem. I think someone has turned on their mic. Please turn off that one. Okay. And the second one is the physically unclonable function. So if I'm designing some logic circuits, in that case they are the problem. But if I'm talking about the physically unclonable function, this process variation becomes one of the benefit, and that can utilize. Please turn off microphone, please. Who is that?
Anil Sharma. Anil Sharma, your microphone is on. Please off it. Anil Sharma.
Either host can mute it, so you can do it. Okay, so if I'm talking about the physically unclonable function, so this was the problem, especially for the logic designs, like process variation was the problem, but this process variation can be utilized to design the physically unclonable function, and that to be used for the security applications. So this becomes the very important thing. Similarly, if we talk about the two random number generators, this process variation in the noise, these are the important thing, and it should not be present in the logic designs. But for the TRNG application, this process variation and the noises becomes the benefit, and that will give you the truly random number. So this is how we can interrelate. Similarly, for counterfeit electronics detection process, we can utilize the aging effects like NBTI. So there are some good thing and bad thing about a different kind of logic structure, whatever we are considering, and that depends on your application. Like if your application is the reliable, then in that case, all these problems, whatever highlighted in the blue, must not be present. But if your application is security, so based on your security component, security primitives, either it is PUF or TRNG or it counterfeit electronics, you need to consider the different kind of these variabilities. Okay, and now this is the last slide. So here we can have, like, I have just embedded all this the previous table into the figure, and if my concern is the security only, in that case voltage and temperature variation need to be avoided, soft error should not be there, aging effect should not be there. But if our constraint is for the reliability, all these things, whatever in the circle, bigger circle is there, that need to be as small as possible. Okay, but these two things like process variation and the random noises, these two becomes the benefit, especially if I'm talking about the security applications. So this is how we can connect the reliability with the security, especially the hardware security. So I'm ending my session from here. So now let me take a few of the questions if you have, and then we can close the session.
Thank you, sir.
Thank you so much. So I think I need to check, is there any
No one has no one has posted the question. I asked for them.
Okay, fine.
Anybody want to ask the question from participants?
Now the forum is open for the question. If you have, you can ask.
I think the lecture was very interesting, exhaustive, and completed all the issues. So no one has any query.
Either it is complete clear or it is nothing is clear. So this
No,
could be the possibility.
it was really good. It was really good from hardware security point of view. Actually, whenever we think about the security word, we generally think about the software security and different layers of networks, but we do not think with respect to this aspect. So it was really good. And especially there are so many candidates are from the electronics and telecommunication department in this FDP. So I think that it will be very beneficial for them, because it opens the new research challenges that how the hardware security and it can be related with the network security and computer security.
Yes. So yeah, all the cyber security is nothing but this is related to the software and the hardware security, and the security itself related to the reliability. So we need to
Yes,
consider
yes,
all the
definitely.
aspects, right? This is important.
Definitely. So thank you so much, sir. You have covered all the aspects of hardware security, different reliability issues, hardware security challenges, and the design considerations. So thank you so much, sir.
Thank you so much for inviting me. Thank you so much.
Thank you,
So I
sir.
think we can close the session now, right?
Okay, you can leave the session. I
Okay.
have one announcement for audience. Now, for the
Okay.
next
Thank you.
session, we will resume at 3 p.m.